Okay, so today's lecture is going to be about optimization. And you'll have to forgive me, I don't remember what the number of this lecture is, but the topic is optimization, and my stupid laptop wants me to install updates. Don't want that. Okay. So, what's the idea with optimization? Well, it's really not so bad. A lot of students are sort of afraid of it when this topic comes up. But really, this is what we've been doing. Uh, for some time. And what do I mean by that? Well, this is just finding absolute mins and maxes. Except the problems, I should say. The problems / examples are applications or word problems, right? These are those cost and profit and revenue and these sorts of questions. So for example, we can ask you to maximize profit. So how we do this is view profit as a function and find the absolute maximum. Or we could ask you to minimize cost. This is view cost as a function and find absolute minimum. Right? So this is all we're doing is, like I say, I've mentioned in lecture a few times that the hard part is not the math. The math has been sort of the easy part of all these problems. It's translating the words into a math problem. That's sort of the difficult part. So what we're going to do to learn these, to really get a good grasp, is look at just a bunch of examples. So let's take a look at a first example here. So suppose a price function is given by P of Q, Q meaning quantity, equals -1/8 Q plus 18 for widgets, whatever these things are that we're selling. And the cost of producing one widget is $6. So the question is, what should we sell the widgets at? What should the price of one widget be? I should probably phrase it that way. What should the price of one widget be? To maximize profit. So since I want to maximize the profit, well, I know how to maximize a function, but I don't know what the function is yet. So I need to find the profit function, right? I need to define it. In the examples we've seen so far, you're given a function and you need to find the maximum or the minimum, right? But in this case, it's hidden in a bunch of language, right? It's hidden within the problem. You have to find the function first. And then once you have it, it's easy, right? Because I just take a derivative, check the endpoints, so on and so forth. So let's remind ourselves what a profit function is. Profit is equal to revenue, the things I bring in, minus cost. Okay, well, revenue is its own function, right? This is price times quantity. And cost, well, it depends. Sometimes I'm given a cost function, and in this case, I'm given what the cost of one widget is, right? So if each thing costs 6, and I'm selling a general amount Q is quantity, then my cost is going to be 6 times Q, right? If I'm selling 3 things at $6 each, I would imagine that it's going to cost me, or I'm sorry, if I'm producing 3 things at $6 each, I would assume that it's going to cost me $18, right? 6 times Q. So here's my revenue function. And a step 2 is to turn the function into a function only involving one variable. So right now we have profit, which I'll just abbreviate by PR, being equal to P times Q minus 6 times Q. But I don't like having P's and Q's floating around in this, right? It's difficult to maximize because I'm used to dealing with things that look like f of x equals something x squared plus something x plus something, right? Any powers of x here, but right, the point is that I want to be able to write this as something in one variable so that I can take a derivative. Right now, if I have 2 variables, it's not clear what the independent thing is. But I have that information, if you'll recall from the problem, that P is equal to negative 1/8 Q plus 18. Multiply that by Q, and I still have my minus 6Q here. Now I have only Q's floating around in the problem, right? So to be more suggestive, I'll write PR of Q. This notation tells me that the independent variable is Q. This is the thing that I'm going to take a derivative with respect to, right? So just simplifying, I'm going to get negative 1/8 Q squared plus 18Q. Ooh, sorry, clicked on something there. Oh, I hate this stupid thing. Okay. Sorry, I write like a baboon when I write on this thing, and I end up clicking buttons that I shouldn't. And finally, simplifying down, I get negative 1/8 Q squared plus 12Q. Great. Okay, so here's my profit equation. I've found the thing that I need, that I want to maximize, and I've turned it into a function only involving one variable. Great. Okay, that completes step 2. All right, well now, let's save that, clear that, and step 3, find absolute max in this case, or min if we're looking for it, right? This is something that we should be comfortable with, right? This was something that was covered in lecture 14.5 or something like that. So we have PR of Q equals -1/8 Q squared plus 12Q. And I want to take a derivative. Oh, yeah, what am I doing? Paying attention. This is -1/4 Q plus 12. And I set this equal to 0. And just like before, we should probably be careful and at least mention this or infinity. But again, there's no domain issues here. We don't have to worry about a denominator being equal to 0 because the only denominator we have is 4. Of course, that's not equal to 0. So I'll just cross that out. You won't need to write this on an exam if it's obvious that you don't have to worry about it. So we set this equal to 0, and I get that 1/4 Q is equal to 12 by just bringing that guy over to the other side, and then multiplying by 4. So this gives me Q equals 48. Okay, so I found the location. I found the location of the absolute max. But notice that this isn't the absolute maximum, right? It depends on what the question is asking. So this is our next step. Step 4 is answer the question. The question was asking, what should we sell the widgets for, the widgets at, to maximize profit? So we found how many. We found the quantity which maximizes profit. So there's an extra step here. To find the proper price, right? What should we sell? We need to take the Q that we found, Q being equal to 48, and plug it into the price equation, right? The quantity gives us the price, and that's what we're looking for. So I take the 48 and I plug it into my price equation, which you'll remember is plus 18 here, right? And now I just simplify and I find my answer. So 48 divided by 8 is 6. 6 plus 18, and that's equal to 12. And I guess I'll have a dollar sign just to have some sort of units. So $12 is what we should charge, is what we should charge for one widget. Okay, so one thing that you may be asking yourself, or at least you should be asking yourself, is, well, how do I know that the point that I found is actually a maximum, right? We always have to test, right? Just finding a critical point doesn't guarantee it's a maximum, right? It could be a minimum, right? It could just be any old critical point. It doesn't necessarily have to be a min or a max. So how do we check? So the final thing we need to do is check. And you can do this certainly earlier in the process. This is just me forgetting that I need to do this. It's very easy to forget this, and I personally forget it all the time. But we need to check that the critical point, because that's essentially what we found, right? The critical point we've found is what we need it to be. And in this case, a max, right? If it's a max, then it's an absolute max in this case. Okay, so how do we check? Well, this is where the second derivative test really helps out a lot. Because the functions typically are going to be quadratics, maybe cubics that we're dealing with. So the second derivative is either going to be a term with just an x, or in this case, a q in it, or it's just going to be a constant. So it's going to be really, really super easy to check. So I would recommend doing this. You could probably do the first derivative test. It's just a lot more complicated. Significantly more complicated. Maybe not a lot, but it certainly makes a difference. So we need to evaluate the profit, and we need to take its second derivative at a general q. So let's just, for the sake of having it on the same board, look at just the original profit equation. And this was -1/8 q squared plus 12q. Okay, so of course, the first derivative we've found already. This is just -1/4 q plus 12. So that means that the second derivative is just -1/4. Okay, now the question is this greater than or less than 0? And it's pretty obviously less than 0 for all q. So if I plug in the critical point, which I don't have written down, but it was 48, right? Here I'm looking for the q value at the critical point, so the location of the critical point. This is still going to be -1/4 because it's not dependent on my value of q. So this is less than 0. Therefore, q equals 48 corresponds to a maximum. And since this is the only one, right, this is the only critical point that exists, and it's a maximum, it has to be absolute. Meaning it's not local, right? Because the picture, the graph of the profit, I'm sorry, this should be PR here. The profit equation is going to look like this, right? And of course, this is probably going to be bounded, right? We didn't discuss the domain of this function. It certainly has a domain. It's not going to be everything. But basically, the point is that the only time this function ever turns around is at this point here, and it's a maximum. So it has to be a parabola of some kind, which is not surprising, right? Q squared. And it only has this one critical point, so it has to be the absolute maximum. There's no local maximums in this, there's only one. Okay, so this just guarantees that this is what we're looking for. So our answer of P equals 12 is what we're looking for. And this tells us that we're good to go. So I'll do that. And I actually found out how to make new slides in this, which is great. Okay, so let's take a look at another example. Okay. Same sort of idea. We're going to maximize profit. This one I'll go through a little bit quicker, just because it's essentially the same idea, just a different function. If price function is given by P of Q equals 38 minus 2x. Oh, crap, not x, sorry. Q, right? Q. And cost function, this time I have a cost function, not an explicit cost for each thing, is C of Q, keep writing X, is 100 plus 20X plus X. God, why do I keep doing that, Nick? Pay attention. There we go. Q's, right, for quantity, plus Q squared. Yeah, okay. So we want to maximize the profit. And the question explicitly is, what is the maximum profit? So this is where it differs a little bit, the maximum profit. In this case, we're not looking for the price which gives the maximum profit. We're looking for what the profit actually is once it's maximized. Okay, so one little note, this is something I didn't mention last time, but we can talk about the domain. And it's simply that Q has to be in 0 to 19, right? Q, of course, you're not going to sell 0 things. That's, first of all, it's not going to maximize it. Second of all, you're not, it seems unreasonable to sell 0 things. And then 19, strictly because my price is never going to be negative, right? And it turns out that the zeros of this function, there's only one, is 19. So we're never going to have a price of 0 or less. So of course, Q needs to be less than 19, right, for this to make sense. Just a little side note, something to notice. And it's also worth mentioning that these are open brackets, so we don't have to worry about checking endpoints here. Okay, so just like before, our first step is to write out a profit equation. This is still revenue minus cost. Revenue is still P times Q. And in this case, I have a cost equation. So my price formula is 38 minus 2Q. And I have a Q on the outside times Q. That stays in there because I want this to be just a function of Q. Everything else is written in terms of Q. And I have to remember parentheses. Plus 20Q plus Q squared. All right, so distributing, I get 38Q minus 2Q squared minus 100 minus 20Q minus Q squared. And combining like terms, I get negative 3Q squared plus 18Q minus 100. Great. Here's the function, and I want to maximize it. Great. So I have the first derivative, and I want to compute it. This turns out to be what? Negative 6Q plus 18. And I set this equal to 0. I won't write or infinity. This is clearly never going to be undefined. So I just need to solve it. And I get Q equals 3. Great. So this is the location of the critical point. Okay, so I'll do this in a slightly different order. Let's verify that this gives a maximum. Let's verify it first, just because we're already sort of in the spirit of taking derivatives and whatnot. So my second derivative is, again, extremely easy. And this is just another example of why the second derivative is so useful here. Less than 0 for all Q. So the second derivative evaluated at 3 is still negative 6, is still less than 0. And we have a max at Q equals 3. Great. Which is what we want. So now all we need to do is answer the question. We found the location of the thing, but we need to make sure we answer the question. Remember that the initial question was, oh, right here. What is the maximum profit? That should have a question mark there. What is the maximum profit? So we found how many we needed to sell to maximize the profit. So now all I need to do is return to the original profit equation and plug in 3. So this is -3 times 3 squared plus 18 times 3 minus 100. All right, so this is 9 times -3 gives me -27. 18 times 3 is 54, I believe. I think that's right. And then I have minus 100. Okay, so 54 minus 27 is -20, or is positive 27. 27 minus 100 is -73, and this is correct, right? So the maximum profit is -73. So this is certainly not a realistic sort of a problem, right? If you're selling something and the most profit you're going to make is -$73, you probably should try a different business. So now we're going to talk about something called area optimization. This is really just the same idea. It's just sort of a more complicated version of it. So all we're going to want to do really just is optimize functions, i.e. find min or maxes, that deal with area and volume. Now you may say this is exactly what we've been doing, just in a different flavor. And it sort of is. The problems, I guess exercises is probably the better way to say it. The exercises are require a little more work and background knowledge to find the function we want to optimize. Right. So really what I'm saying, as I've said, is it's a more complicated example. But we have a nice set of steps that we can sort of follow. But so the first one we want to do is find the important formulas. Right. This is things like profit, right? Area or volume. Things like this, right? Things that we sort of need to know the formulas of. We need to know the volume of a box. We need to know the area of a rectangle formula, things like this. And then we want to use what we know, use these formulas correctly to write the, I'll say optimization formula. This means like if we're trying to optimize cost, for example, we want to write cost in terms of one variable. And this is similar to what we did last time, right? We wanted to write everything in terms of Q, in terms of quantity. Okay? Then we want to find the critical points, just as we've done. And this is easy. Take a derivative, set it equal to 0, right? Go through that whole song and dance. And then we want to interpret our answer, meaning answer the question. Okay. Now, you may be saying this is exactly what we did last time, and it is. The issue is that this part here is a little bit more complicated, and there's a little bit more knowledge required for number one. So I think, especially in these examples, it's very important to keep this list in your head because the problems do get complicated very quickly. All right, so let's take a look at sort of a classic example. This is the one that you'll typically see when you look at problems of this type online or anywhere else. Let's minimize the cost of a rectangular box with open top with length which is twice the width. The material on, the material on the sides costs $6 per square foot, and the material on the base costs $10 per square foot. The volume of the box needs to be 60 cubic feet. Okay, now the question. Find the dimensions of the cheapest box. Something like this. This is sort of a nice standard example. All right, so let's start decomposing this. First of all, first thing I want to notice, all right, minimize. We're looking for a minimum here. Great. Cost. We need a cost function. This is the thing that we're minimizing, right? So one of the first things we need to do, one of the important formulas in that step one, is going to be the cost formula. All right, rectangular box. That's going to help us figure out what sort of area and volume formulas we need, right? Open top means that, well, there's no top, right? When we're counting up surface area, we're going to have to deal with surface area in this case. We don't count the surface area that would be accounted for by the top, right? Just the bottom and the four sides. All right, length is, well, I'm drawing right through this. Hang on, I'm gonna hit undo there. Length is twice the width. Can't draw a straight line. Okay, so this helps with our dimensions. This is gonna help us find out the surface area. It's gonna help with coming up with the formula for this. The material on the sides costs $6. And the material on the base costs $10. This is going to help us find the cost formula. And finally, the volume needs to be 60 cubic feet. And then finally, we want to find the dimensions, right? So when we actually have our answer at the end, we want dimensions. We're not looking for the total cost. We're not looking for the total surface area. We're looking for the dimensions of this box, whatever box minimizes this. Okay, so step one, find relevant formulas. Okay. Well, a picture helps. So let's start with a picture. And I'm going to draw this in like the worst possible way. That, and there, good enough. Fine, and I'll draw lines on the inside like this to signify that it's an open box. There's no top, right? Okay, and let's call this W, this length here. So this will be the width, this will be the length, and then this will be the height, right? Great. Okay, so what do we know? Well, we know that length is equal to twice the width. This comes right from the problem. Okay? And sort of hidden in here is, because it's a rectangular box, it means that this side here is equal to this hidden side back here, right? This length is equal to L, and this width here is equal to this width back here, right? Because a rectangle has this symmetry. And of course, H carries through the whole way. Right? You don't want like a lopsided box. Okay, so we have L equals 2W. I don't want to deal with cost quite yet. It seems like that'll be sort of a lot. So let's deal with something a little bit easier. The volume needs to be 60 cubic feet, okay? So the volume of a box is length times width times height, right? Just multiply the three dimensions together. And this needs to be 60. So this is sort of a restriction that we have. Okay? Now let's deal with cost. And this one's going to be a little bit of work. So let's call this side here the front side. Front. And I'll call this the right. I'll call this back. This will be left. And down here on the bottom will be bottom. Okay, just so we can sort of organize and see where everything is coming from. Okay, so we know that the side faces, and what do I mean by the side faces? I mean front, right, back, and left. We know that the material for these costs $6 per square foot. Okay, well, I find the square foot dimensions, meaning just the area of each of these, by multiplying base times height in each case. Okay, so let's find the cost of the front. This is cost of front plus cost of right plus cost of left plus cost of back plus cost of bottom. And let's build these up one at a time. All right, so front is going to correspond to width, W, times H, height, right? W times H, but then for each square foot, right, for each unit of area, I have $6. So just like with cost before, if I was selling Q things and it cost me $6, I would have 6Q. In this case, I have a whole area that costs 6 per square foot. So I take the area and I multiply by 6, right? $6 per square foot. Okay, how about the right side? Well, this is L times H, and again, the cost is still 6. So this is L times H times 6 plus left is exactly the same thing, right? Because this is H, this is L, because it's parallel to this. L times H times 6 plus, now the back has W as its horizontal dimension, and then multiplied by H, W times H plus 6, or times 6. And then bottom is a little bit stranger because I don't have an H. I have W times L, right? This is the dimension of this rectangle on the bottom. W times L times, but now it's not 6, right? Because the base costs different than the sides. The base costs 10. So this is W times L times 10. Great. All right, so I can simplify this, right? This is nice and easy. 6WH, I can even do this all in one go. I have a 6WH and another 6WH, so that's 12WH. I have 6LH plus 6LH, that's plus 12LH. And then finally 10WL. Great. So this is my cost function. And I think I'm done with step 1. Seems reasonable. Now, moving on to step 2. I want to turn the cost function, right? Because this is the thing I want to minimize, into a function of one variable. Okay? So I'm going to use the relationship L equals 2W to figure this out, right? And I'm also going to use 60 is equal to LWH. Now, how am I going to do this? All right, well, let's do this in steps. So a little mini step here. This will be corresponding to just making this substitution in the cost function. So remember, cost was equal to 12WH plus 12LH plus 10WL. Okay, using this substitution, I can rewrite this now as each time I see an L, I replace it with a 2W. So I still have 12WH, nothing's changed there, and then 12 times 2WH plus 10W times 2W. Okay, so I have 12WH plus 24WH plus 20W squared. So this is equal to 36WH plus 20W squared. Great. Problem is, this still isn't in one variable, right? There were 3 variables floating around. I got rid of 1. There's no more L's in this, but H is still here. That's a little annoying because I don't know how to differentiate something with more than one variable, right? There's not sort of an easy way. So I'm going to use this guy now to get rid of the H. And what do I mean by that? Well, if 60 is equal to LWH, I'll use the substitution I used originally, L equals 2W, and I get 2W times W times H, which is, of course, 2W squared H. Okay, well, let's solve for H. Just as I have L in terms of W here, I can get H in terms of W, right? If I just divide both sides by 2W squared, I get 60 over 2W squared equals H. And this is just 30 over W squared. Okay, so now that I have this, I can come over here and write a cost equation, which is only in terms of W, right? So I'm going to take this equation here and write it over here while eliminating that weird H, that thing that's screwing us up, by making this substitution. Okay, so I have 36 W times 30 over W squared plus 20W squared. 36 times 30 is 1080 over W, because this W and this power cancel, plus 20W squared. This is finally my cost function in terms of one variable. Great, that takes care of step 2. Now, the next step is find the critical points, right? My cost function, I'll remind you, is, where is it? Where did it go? 20 W squared plus 1080 over W. Okay, so this is easy. C prime of W is 40W minus 1080 over W squared, right? This is just a chain rule. I suppose you could do quotient rule, but please don't. There's no reason to do it. This is just 1080 times W to the negative 1. Okay, so here's what I have, and I want to set this equal to 0. And I suppose you could ask the question, well, what about when W equals 0, right? This is essentially asking W equals 0, right? Because this, I know I write or infinity, but really this means when is this thing undefined, right? When can I not take a derivative? But ask yourself the question, if we're building a box and it's required to have volume of 60, can the width of that box ever be 0? Of course not, because then the box completely collapses and there is no volume, right? So impossible. It's a good question to ask, but you don't have to worry about it. Okay, so we set this equal to 0 and we solve. How do we solve? Now, this is something that I think a lot of students will struggle with, but it really is not very difficult. So if I have 40W minus 1080, 10, Nick, dum-dum, 1080, right? Good. Over W squared equals 0. I hate this fraction. I really don't like it at all, and I want to get rid of it. Okay, I can do this. Just multiply both sides by W squared. As long as I do to both sides what I want to do, it's legal. I have an equation, so why not? I have 40W cubed minus 1080, and I've essentially cleared the fraction, right? This is a common trick that happens, and you should definitely get comfortable with it because it makes your life so much easier. Everybody hates fractions. You're not alone, but there's a nice way to get rid of them when you have an equation. Okay, so now I have 40W cubed, and I'll have to check my notes because I'm not certain what 1080 divided by 40 is. It is, looks like 27, I believe. I think that's right. Nah, just believe me. Check me. If I'm wrong, then just email me screaming at me. And now to get rid of a cube, well, it's the same thing as getting rid of a square or to the fourth, right? Just take a cube root of both sides. And I get W equals 3. There are 2 things we need to do. First, I'll do it over here, actually. I cannot draw in a straight line. There we go. We need to check. This is a minimum. Sorry. Where's my thing? Undo. Yeah. Why did I write? They both start with M, Nick. Check that this is a minimum. Okay, because we want to minimize cost. So let's take the second derivative. And what do we get? Well, I get 40. And that turns into a plus 2 times 1080. I don't want to do that in my head right now. W cubed. And I want to plug in 3. 40 plus 2 times 1080 over 27. Okay, I have 40, which is positive, plus 2 times positive things, right? This ends up being, well, I know what this is. This is just 40. So this is 40 plus 80, which is certainly greater than 0, right? So because it's greater than 0, therefore, W equals 3 corresponds to a minimum, right? Because the thing is concave up, and this is the only critical point that we found. Okay. So there's still one more thing to do, and this is our step 4. We have that W equals 3, but the question asked us to give dimensions, right? W is only one of the dimensions. So we have to recall that L is equal to 2W and H is equal to, what was it, 30 over W squared? Right. Okay, so I need W, L, and H. But once I have W, I can get all of them for free, right? So this tells me that the L that I'm looking for is 2 times 3, or 6. And the H that I'm looking for is 30 over 9, or 10 over 3. So the dimensions of the cheapest box are 3, 6, and 10 over 3. This is the box which minimizes the cost, and we're finally done.